Let us consider a very simple circuit. We have a voltage source denoted by V with a subscript of S connected across a resistor of resistance value R. What's going to happen is a potential difference is going to get created across the resistor. Let's denote that potential difference by V of t. This is the instantaneous voltage. Instantaneous voltage developed across the resistor R. Cross R. Now, because of this potential difference, a current I is going to flow through the circuit. Let's denote that current I by I's of t. So here our current I's of t is the instantaneous current flowing through the circuit, or simply we can say flowing through the resistor R. So now that we have the information of the voltage across the resistor R and the current flowing through it, we can find out an expression for the instantaneous power. So the expression for the instantaneous power, P of t, is given by the product of the instantaneous voltage and the instantaneous current. Now what we're going to do, we're going to apply Ohm's law. So from Ohm's law we have that the current flowing through a circuit is given by the potential drop divided by the resistance offered by the circuit. So that gives us V of t multiplied by V of t divided by R. So our expression for the instantaneous power becomes V squared of t divided by R. So this is the expression for the instantaneous power. So now that we have the expression for the instantaneous power, we're going to sum the instantaneous power over the time interval t1 less than t less than t2, and that is going to give us, summing the instantaneous power over this particular time interval is going to give us the energy of the signal. So we get the total energy. So that's total energy, which is given by the integration, the lower limit going from t1 to the upper integral, which is t2. We have p's of t times the integrand dt, which is simply the integration t1 going to t2. P's of t will be v squared t over r times dt. So this is how we can calculate the total energy of the given power when the power is given. Now we can also find out the average power value over the same time interval. So the average power P is going to be equals to 1 over the time interval, which is t2 minus t1, integration t1 going to t2, v squared t over r dt. So this is how we can find out the average power of the circuit. Now, using the same idea, in the sense, the convention for the power and energy, we can extend it to any other kind of signal. So we'll be dealing primarily with two types of signals: the continuous time signal and the discrete time signal. So let us consider the first type. So we have x of t. This is going to be a continuous time signal. A continuous time signal is a signal which is going to have values at any given time. So if we have the x-axis as the time axis and the y-axis as the continuous time signal, and assuming that we have a continuous signal, that at any given point of time t1 we're going to find some value of the signal. So that is what is meant by a continuous time signal. For this type of signal, now we consider the time interval. In the interval t1 and t2, given by t lying between t1 and t2, the energy of this continuous time signal is given by E of t is equals to the integration going from t1 to t2. If we recall from in the previous section, we have found out that the total energy is given by something squared, which is the voltage squared over R times dt, so maintaining the same essence. So we can write here as the absolute value of the continuous time signal squared times dt. Now there's a reason behind using the absolute value here and squaring it. So this x of t, majority of the signal that we will be dealing with in signals and systems are going to be complex signals. You can say complex valued signals. So complex valued signals means its conjugate is going to be present. This is the conjugate of x of t. Then when we take the product of the signal with its conjugate, that is the same as saying we take the signal, the absolute value of the signal, and square it, and this value is a real value. Or you can say it's a real valued function. So this is one primary reason why we are taking the square of the absolute value for finding out the energy. So we can also find out the power of the signal. So the power will be given by 1 over t2 minus t1, integration going from t1 to t2, the absolute value of the signal squared times dt. So this is going to be the average power. The average power value. Now if we look at the discrete time signal, so if we consider a discrete time signal x of n, so this is a discrete time signal. So that would mean a discrete time signal means, so we have our x-axis, let this x-axis be the discrete time axis denoted by little n, and we have the y-axis, and this is where the function x of n is going to lie, the values of x of n is going to lie. So a discrete time signal is going to have discrete values. So this is 0, n equals to 1, 2, 3, 4, 5, and on the negative side we have -1, -2, -3, -4, -5, and so on. So a discrete time signal is going to have values only at discrete time intervals. So we can say, let's say this is having a value of 1, a value of 2 at n equals to 1, it has a value of 2 at n equals to 2, it has a value of 2 at n equals to 3. So these are all examples of a discrete time signal. Now, so this continues. So in order to find out the energy of a discrete time signal. So that would be simply E's of n will be equals to the summation of small n going from n1 to n2, the absolute value of the discrete signal squared. And to find out the power of the signal, which will be the average power, that simply equals to 1 over the time interval. So the time interval will be n2 minus n1. But here n2 and n1 are both included, but when we are subtracting n1 from it, so we have to account for the fact that we are not taking n1, so we have to add 1 unit to it, multiplied by the summation n going from n1 to n2, the absolute value of x n squared. So this is the expression for the power signal for the discrete time signal x of n. There will be systems in which we will be more concerned about examining the power and energy of the signal over an infinite time interval. So when you have an infinite time interval, then in order to calculate the energy, we have negative infinity to positive infinity, the absolute value of the signal, which is x of t squared dt. So this is for the continuous case. However, for calculation purpose, we will be using the limit t going to infinity, and the limits will be from negative t to positive t, the absolute value of x of t squared dt. So this is for the continuous time case, for the continuous time signal. And if we are considering the discrete time signal, then we have a infinity given by summation negative infinity to positive infinity summed over the signal x of n squared, or we can say the limit n going to infinity, the summation small n going from negative n to positive n, the absolute value of the discrete time signal squared. So this is the case for discrete time signal. However, we have to be a little bit careful here whenever we are calculating the energy. So in some cases, for some particular values of xt or x of n, we have to be careful that this integration must converge, because in certain cases the integration does not converge, and that would mean we'll have to move on to the average power value. Whenever the energy of a signal is infinity, that means the integral is not converging, then we have to consider the average power of the signal. Now let us consider a continuous time signal given by the unit step function u of t. Now the unit step function is defined as a function which has the value of 1 for all values of t greater than or equals to 0, and it has a value of 0 elsewhere. So if we plot this, so let's consider the x-axis as the time axis t, and we have the y-axis, which is going to be the xt axis, then our unit step function is going to look something like this. So this function has a value of 1 for t equals to 0 or at t greater than equals to 0, and it has a value of 0 for t less than 0. So let's try to find out the energy of such a signal. So we have energy given by E infinity is equals to limit t goes to infinity, integral negative t to positive t, we have use of t, which is the absolute value of the unit step function, squared dt, which is equals to limit t going to infinity. Now we can decompose the integral into two parts. So we have negative t to 0. So as per the definition, the function use of t has the value of 0 in this particular limit. So we have absolute value of 0 squared dt plus the second part of the integral. It starts at 0 and goes up to t. So here in this interval from 0 to t, the step function has a value of 1. So we have the absolute value of 1 squared times dt, which is equals to limit t going to infinity. So the first integral is going to be 0. So we're left with the second integral, which is 0 to t dt. So we have finally limit t going to infinity. So the integration of dt value is simply t, and we have limit going from 0 to t. So that gives us limit t going to infinity, and facing the limit we have upper limit minus the lower limit, which simply gives us limit t going to infinity and t, and this value is infinity. So that means we have a signal whose the unit step signal whose energy value is infinite. That is because this integral does not converge. So in order to find out a more meaningful way to express this energy, we go to the average power value. So we'll try to find out the average power. So the average power will be equals to limit t going to infinity. So we have to divide it by the interval, which is 2t, and the limit goes from negative t to positive t. We have the absolute value of the unit step function squared dt, which will be equals to limit t going to infinity, 1 over 2t. Like in the previous case, we decomposed the integral into two parts. So from negative t to 0, we have the absolute value of 0 squared, that is the value of the unit step function, times dt, plus the second integral, which goes from 0 to t, and in this particular interval the unit step function has the value of 1, so we have 1 squared times dt. So that gives us limit t going to infinity, 1 over 2t, the first integral is 0, plus this integral is simply t, so we have the limit going from 0, this is small t, going from 0 to capital T. So that gives us limit t going to infinity, we have 1 over 2t, and using the limits we get t. So the t and t gets factored out, leaving us with limit t going to infinity, 1 over 2. So this gives us the average value of power is equals to the limit of t going to infinity, half is simply half. So now we are getting a value. So this is the average power of the unit step function calculated over an infinite time interval. Let us consider another example. So let's say we have a continuous time signal xt given by the value, it has the value 1 in the limit of the time t lying between 0 and 1, and it has a value of 0 elsewhere. So if we plot the graph, so this will have the time axis, and we have the xt axis, the y-axis, and we have the value. The function assumes the value 1 in the limit 0 to 1, and it's 0 elsewhere. So what will be the energy of this particular signal? So we'll find out the value. So we have limit t going to infinity, limit negative t to positive t, the absolute value of x of t squared dt, which gives us limit t going to infinity. So we have the function existing only between the limits 0 and 1, and the value is 1 dt. So we do not have to consider the other values of the limit. So we have limit t going to infinity, integration of 1 dt is simply going to be t, the limit from 0 to 1. So that gives us limit t going to infinity. The value is simply 1, which is equals to 1. So here we have a value, we have an energy value which is finite. This is a finite energy signal. Now let's try to find out what's the average power value of this particular signal is going to be. So we have P infinity is equals to limit t going to infinity 1 over, this is the average power that we're talking about, so we have 1 over 2t, the limit going from negative t to positive t, absolute value of the signal squared, times dt. So we have limit t going to infinity 1 over 2t. So we have the function existing only between 0 and 1, rest here elsewhere it's a 0, so we have 1 squared times dt. So that gives us limit t going to infinity 1 over 2t times t, the limit going from 0 to 1. So that simply gives us limit t going to infinity 1 over 2t times 1, so that is simply 1 over 2t. And when we place the limit, so we have 1 over infinity, which gives us 0. So that means when we are having a finite energy signal, the average power value is 0, while in the previous case, in the previous example, we found out that when we have an energy signal having infinite energy, it's going to have some finite average power value. Let's do another problem and check when the energy value is infinite, but this time we're going to take the case of a discrete signal. So suppose we have a discrete time signal x of n given by the value x of n is equals to 4. So the graph of this discrete time signal is going to look something like, at n equals to 0 is going to have a value of 4, at n equals to 1 it's also going to have a value of 1, at n equals to 2 it's going to have a value of 4, at n equals to 3 it's going to have a value of 4, n equals to 4 it's going to have a value of 4. Let's redraw it. So we have a value of 4. Similarly, we have n equals to 4 at negative 1, negative 2, negative 3, and negative 4. And this is going to continue all the way up to infinity. So we have our range of n, or the interval of n, lying between negative infinity and positive infinity. So this is the value of our discrete time signal. Let's try to find out the energy of the signal. So the energy of the signal is going to be given by limit n going to infinity summation small n negative infinity, it's negative n goes to positive n summation of 4 squared. So this is equals to limit n going to infinity sigma small n going from negative n to positive n 16. So this simply means that we are adding 16 to 16 an infinite number of terms, both in the positive infinite direction as well as in the negative infinite direction. So addition of this is going to give us an infinite value for the energy signal. So now we try to calculate the average power value. So the average power value for this infinite range will be equals to limit n going to infinity 1 over, so we have the upper limit which is n minus the lower limit which is negative n, and we have to account for one of the value which is plus 1 times sigma n going from negative n to positive n, we have 4 squared. So that gives us limit n going to infinity 1 over 2n plus 1. So summation 4 squared is, so here we see that the index n is symmetric over the y-axis. So instead of running it from negative n to n, what we can do, we can run it from 0 to twice of n, and that would mean the same thing. Then we have 16 here. So that gives us equals to limit n going to infinity 1 over 2n plus 1. So we have 16 added to 16 added to 16, and this runs for 2n times. So this gives us simply limit n goes to infinity 1 over 2n plus 1. We have 16 times 2n, which is equals to limit n goes to infinity 2n over 2n plus 1 times 16. Now we're going to divide the numerator and the denominator of the fraction by 2n. So that gives us limit n going to infinity. So we have 1 divided by 1 plus 1 over 2n times 16. Now substituting the value of the limit, so that gives us 1 plus 1 over infinity times 16. So we have 1 over infinity is 0. So that gives us 1 divided by 1 plus 0, which gives us 16. So this is the value of the average power. So for this particular example, we got the energy value to be infinite, whereas the average power value is simply 16. It's a finite value. Let us do one problem. Let's say we have this continuous time signal given by x of t is equals to e raised to the power negative 2t times u of t. We have to find the value of the energy signal and the power signal, and the average power value calculated at infinite intervals. So let us begin. So we begin by finding the energy value first. So we have energy, the integration going from negative infinity to positive infinity times the absolute value of our function xt squared times dt. Now we know that ut has the value of 1 for t greater than equals to 0 and 0 elsewhere. So that would mean we can break down this integration into two parts. So from negative infinity to positive infinity, we have the absolute value of e raised to the power of negative 2t times ut value is going to be 0 squared dt plus integration 0 to infinity e raised to the power of negative 2t times 1 squared dt. So this gives us 0. The first integral will be equals to 0 plus 0 to infinity e raised to the power of negative 2t times 2 is going to be negative 4t dt. So the integration of the exponential function is going to be e raised to the power of negative 4t divided by negative 4 with the limits going from 0 to infinity. So we have negative 1 over 4 common. Now we take the limit, so we have e raised to the power of negative 4 times infinity will give us negative infinity minus e raised to the power of negative 4 times 0 will be simply 0. So this value will be equals to negative 1 over 4 times, so e raised to the power infinity, this tends to 0. So we are left with e raised to the power of 0, which is 1, negative 1. So the final value of the energy is going to be 1 over 4. Now let's try to find out the value of the power. So our power value will be equals to limit t going to infinity. We have 1 over 2t integration going from negative t to positive t. The absolute value of e raised to the power of negative 2t times u of t squared dt, which will be equals to limit t going to infinity 1 over 2t. So we can break down the integral. So the first integral will have the limits going from negative t to positive 0 to 0, simply 0. So this value will be e, absolute value of e raised to the power of negative 2t times 0 dt plus 0 to t e raised to the power of negative 2t times 1. Now we have the value of ut to be equals to 1 because as per definition it has a value of 1 when the value of t runs from 0 to infinity. Now t is, we're considering a t goes to infinity, so that's why the value of u of t, the step function, is assuming the value 1 squared dt. So this will be equals to limit t going to infinity 1 over 2t. So the first integral is 0. We are left with the second integral, so we have 0 to t e raised to the power of negative 4t dt, which is equals to limit t going to infinity 1 over 2t, and the integration of the exponential function is going to be e raised to the power of negative 4t divided by negative 4, the limit going from 0 to t, which is equals to limit t going to infinity 1 over 2t times e raised to the power of negative 4t divided by negative 4 minus e raised to the power of 0 divided by negative 4. So we have limit t going to infinity times 1 over 2t. So we rearrange it. We have 1 over 4 minus 1 over 4 times e raised to the power of negative 4t. So that gives us limit t going to infinity. We factor out 1 over 4, so we have 1 over 8t multiplied to 1 minus e raised to the power of negative 4t. So when we substitute the value of t, when we use the limiting value of t, so we have 1 over 8 times infinity, which is infinity, 1 minus e raised to the power of negative infinity. So this value is going to be 0, this fraction is going to be 0, is going to be 0, so that finally gives us 0 times 1 minus 0, which is equals to 0. So this is the value of the average power for the given signal. X of t equals to e raised to the power of negative 2t times the unit step function. So far we have worked on 4 problems. So let's list all of them. So we have a continuous time signal given by the unit step function u of t. Here we have found out that the energy value is equals to infinity, while the power value was a finite value equals to half. In the second example, we consider that we have a continuous time signal whose value is 1 and its energy value was found out to be 1 and its power value was found out to be equals to 0. In the third example, we considered a discrete time signal x of n equals to 4, and we found out that its energy value is equals to infinity while its power value is equals to 16. In the fourth example, we considered a continuous time signal given by e raised to the power of negative 2t times the unit step function. For this function, we found out that the energy value was equals to 1/4 and its power value was equals to 0. So based on all these 4 different types of examples, so we can identify 3 important classes of signals. So we have 3 classes of our signals. So our class number 1. So in the class number 1, where we have signals with finite energy, signals having finite energy and 0 average power. So such signals are referred to as energy signals. So these class 1 signals are called the energy signals. So these signals are going to have a finite value of energy, but the average power value is going to be 0. So from our 4 examples, so wherever we are having finite values of energy, so we have the continuous time signal xt equals to 1 having the energy value equals to 1. So this is a finite value. So this belongs to class 1. So this is a energy signal. We can see that its average power value is 0. Now for this fourth type, where the continuous time signal is given by e raised to the power of negative 2t times the unit step function, this one also has got a finite energy value and a 0 average power value. So this is also an energy signal. Then we have a second class. So the class number 2, these type of signals have infinite energy values, but some finite, but they have got some but finite power values. Finite average power values. So if we look at our example, so we have xt equals to the unit step function. So this has infinite energy, but it has got finite power average value. So this is going to be referred to as a power signal. Similarly, when we consider the discrete time signal value of 4, so here we see that the energy value is infinite while the power value is finite. So this is also going to be a power signal. And we have the final category or the final class, the class number 3. This includes signals which have neither finite energy nor finite average power. Neither finite energy nor finite average power. So we're going to encounter these kind of energies, these kind of signals later on. One example includes if x of t is equals to t. You can check it out. You can find out the energy value as well as average power value. You'll see that it's not going to satisfy either the condition as given by class 1 or the condition given by class 2. So the outcome of today's lecture is that we can categorize any given signal into two categories. So it could be either a power signal or it could be an energy signal. One thing that we can note here, that if the signal is going to be a power signal, it is not going to be an energy signal, and vice versa. So here we can see the first example. So this example where xt is a unit step function. So our unit step function is a power signal, but it is not an energy signal. And when we have these continuous time signal value equals to 1, then it becomes an energy signal, and its average power value is going to be equals to 0.